Okay, we're coming to the end of chapter 2 in the algebra textbook. In this video, we're going to go through the final section, section 2.8, which is on algebra of functions and function composition. So I remember when I was learning this topic in school, it seemed kind of unnecessary. I didn't see the point of it. And so just to give you some motivation for how this would be applicable, as we're going through this section, don't think of a function from this standpoint. It's like, if you have y is equal to the square root of x, well, the graph of the square root of x it passes the vertical line test, so this is a function. You could write this as a function. Don't think about it that way. Think about it from the standpoint of more permanently defined functions that have been created and they're more permanent to a situation. Okay, so a couple of sections ago, we talked about a cost function. So so maybe you have a cost function in a manufacturing plant. It's a permanent function. Like you've named it, right? You might even name a function. You might create a function and name it. A function for some application, and you name that function. You'll see functions like in Excel. You can input all kind of different functions, right? We talked about a couple of videos ago the Heaviside function. In coding softwares, you can make functions like functions in MATLAB. You can name the function whatever you want. So it's a permanent function. It exists. It's more, it doesn't just vanish after you use it, if that makes sense. So here's kind of an example of that. Again, in section 2.5, we talked about the idea of a cost function. And so it was the cost to manufacture a certain amount of items. If you're going to manufacture 100 of these items, how much does that cost? 150. You input the amount of items you're going to manufacture, and it gives you the cost to manufacture those items. That's C of X. And then there's a revenue function. It's the revenue that you get from selling X amount of items. Okay, to get the profit function, you subtract the revenue function from the cost function, or you subtract the cost function from the revenue function. So you see, might not be the best example, but you could just be in a situation and you've got these permanent functions that you've created, and then you're trying to get an idea. Okay, what if I combine these functions? What would I get? What if I did a composition of these functions? What would happen? We'll talk about function composition in a second. Okay, so that's the idea. What we're talking about in this section is algebra of functions, so adding, subtracting, multiplying, dividing functions, as well as function composition, which we'll talk about in a little bit. All right, so the sum, difference, product, and quotient of functions. The notation is, so it's just like it sounds. It's like here, you're subtracting the cost function from the revenue function. You could add two functions, subtract two functions, multiply two functions, divide two functions. And the notation is like this. Okay, so as far as this here, this profit, it would be the profit function would be equal to R minus C of X. You see, that's the notation. If you were multiplying, you would just put a multiplication symbol. And if you were dividing, you would do, if you wanted to divide the revenue and cost function, you would do like that. And that would be, you don't have to, again, it's just not a math channel for math majors. You don't have to do any of this. All you really need to understand is just the idea of combining functions, but this is the official math notation for it, as shown here, for adding, subtracting, multiplying, and dividing. And all you're doing is you're just adding two functions together, subtracting, it's just like it sounds. A function is just some expression of X, right? You know how to add two expressions of X, subtract them, multiply them, divide them. Okay, but what about the domains of the resulting function? Well, okay, here's the rule for the domains. Really simple. For any combination of functions, it's all the same if you're adding, subtracting, multiplying, or dividing. If you're combining them in any way, in any kind of algebraic combination. So let's come back to here again. Okay, so if you're doing R minus C of X, okay, what's the domain of this? So take the domain of the R function, take the domain of the C function, and it's wherever they overlap. Because if you have this value, well, that's not in the domain of the R function. if you have a value here, that's not in the domain of the C function. So how you, if it's not, if the function, if you chose this number and you tried to do R minus C, well, the R doesn't exist here, so you can't use it, right? If you try and subtract R minus C with this value, well then, okay, no, then C doesn't exist. You would get a number for R, but then C, it would be R something, whatever R of this minus doesn't exist. Now there's only one caveat in that if you're dividing, then whatever the denominator is, you can't include whatever makes the denominator 0. So for this case, it would be the intersection of f and g, provided that g of x is not equal to 0. That's the only caveat. And that's it. It's not like there's different rules if we did this, if we added these, or if we multiplied these, there would be different rules. No, it's still this is the domain rule. It's only if you're dividing them, it's the same domain rule, the intersection, but then the denominator can't equal 0 as well. That's it. And again, all the domain is about is just you can't do any kind of adding or subtracting or multiplying, dividing of functions unless both of the functions exist for that input. That's the idea. And also, there's no domain issue when it comes to dividing. There's no domain issues with adding or subtracting or multiplying, but there is with dividing. You can't divide by 0. Okay, so adding two functions. F of x is equal to square root of 25 minus x squared. G of x is equal to 5. F plus g of x is square root of 25 minus x squared plus 5. That's it. Okay, here they give 3 different functions, and they do some algebra. So m minus n of minus 2. M times p of 1, right? They give m, n, and p, 3 different functions. And so we're going to work a bunch of example problems like this, but it's really easy. Okay, combining functions and determining the domain. We just talked about this concept. We'll work example problems in the next video, but it's very straightforward. Determine the domain. If you're combining 2 functions, so p divided by n, what would you do? If the function p divided by function n of x, write out the domain of p, write out the domain of n. Where do those intersect? That's the domain, but also you got to include anything that would make n 0. If you're just adding, subtracting, or multiplying, then you don't need to think about something equaling 0. It's just where do the 2 functions intersect. That's it. And you can think about all these concepts we've talked about. You can extend this if you wanted to add 3 separate functions, 4 separate functions, whatever. It's a simple extension. You can combine functions algebraically in any way you want, 2 or 3 or more functions in any way you want. So if I had, some composition where like f divided by g plus h minus m of x. Okay, you can do this. It's no problem. These are all just expressions of x. Just combine them. But what's the domain here? Well, each one of these has to exist. When you input x, you can't have m not exist, or h not exist, or f not exist, or g not exist. That can't happen. But then also you can't divide by 0, so g can't be 0. You see? That's the idea. All right, we'll work example problems on determining the domain. Evaluate a difference quotient. We're not going to go into this. This is a calculus concept. I'm not sure why they show that here, but okay, compose and decompose functions. What do they mean by compose? What they're saying is, so if we had a revenue function and we had a cost function. If I wanted to, I could say, what is R of C of X? I don't know what this means. This probably has no meaning. But that's the idea. You're putting a function inside of a function. That's what they're talking about as function composition. And function decomposition, all they're talking about there is you're looking at an expression of x that's already had some sort of composition done to it, and you're trying to go in reverse and see what you're trying to decompose it and see, okay, what was the function composition here, right? You've already put a function inside of a function and simplified it. Now you're trying to decompose it and recognize what was the function composition that was done to get here, to get to this expression. Okay, so the composition of f and g, denoted f with this circle g, is, so this would be, this here you would write it as R circle C of x. That's how you would, that's the notation for this. C is inside of R of C of x. So like think of it like this, R of C of x, so you do R of C of x. That's the idea. Okay, and just to give you an idea of the purpose of this, I don't know why you would ever put a cost function inside of a revenue function, but maybe you know, I don't know what the function is. It could be anything. You've got some functions that you have, and you might want to compose them. And you might say, well, why would I go through all this notation stuff? Like, this is so complicated. Yeah, you're right. If you just had f of x is equal to x squared, and f of x is equal to, you know, sine of x, well, okay, well, why you don't need to do all this notation, or this would be g of x, let's say. All that notation seems unnecessary. But if you've got more permanently defined functions that are like, you know, you've created these functions, they're permanent. They've got names to them, right? You name the function. This is whatever of x. You know, they're named. Well, then you might want to leave it like, you might want to look at it this way. Okay, if I compose this function within this function, what do I get? The idea is it's like the output of one function is the input of another function, right? You might want to keep track of the functions of, okay, what's the output coming out of here is going into, it's like a machine, right? You might want to look at it like a machine. The output of this function here, of whatever this is, this could be really complicated, like a, you know, whatever. That output is going to be the input to some other function. That's the idea of function composition, right? They show this here. Input x, g of x if that's applied to g of x, the output serves as the input into another function, and you get an output. That's the idea. And so they give some examples here. F of x is equal to x squared plus 2x. G of x is equal to x minus 4. And so you do f of g of 6, g of f of minus 3, and then they do f of g of 0. So we're going to work a bunch of examples like this. Okay, what about the domain? So the domain of f of g is the set of real numbers x in the domain of g such that g of x is in the domain of f. So that's a kind of confusing statement. The set of real numbers, so first of all, let's reason through this. First of all, if we start with c of x has to be in the domain of c, or else you're going to get does not exist, right? That's obvious. So anything in the domain of C is part of the domain of the composed function, the composite function. But okay, but C has a range, right? So it's the domain of C, and then and also the range of C that is within the domain of R. I don't know if that's the best way to say it. The set of real numbers x that's in the domain of G, which is C here, such that G of x is in the domain of F. I mean, that's all math talk, but I mean, you get the idea. If you have, so everything in the domain, let's start here. Everything in the domain of C. If it's not in the domain of C, then it's not going to work, obviously. But the domain of the composite function is potentially going to be more restricted than this, right? Because the idea is there's going to be a subset of this domain that when you evaluate C of x, you get a number that is within some subset in the domain of R. This is all really mathy talk, but so you can input any x that's in the domain of C, but then if C of x needs to be in the domain of R. So that's the idea. I don't know how to say that in the best way mathematically, but I think you get the idea. So let's look here. So here's f of x, g of x. F of x is 2x minus 6. G of x is 1 over x plus 4. F of g of x is 2 times 1 over x plus 4 minus 6. You see how they did that? They put g of x, they replaced x with g of x. Simplify and you get this. Okay, so what's the domain of G? What's the domain of G? X is not equal to minus 4. Okay, so that's part of the domain of the composite function. Now you look at the composed function and say, is there any, we know x can't be minus 4, but now is there any other x value that would cause the composite function to not exist? Then that's outside of the domain as well. Okay, so we're going to work examples and you'll get a better feel for this. Okay, here's another example. Here's m of x, here's p of x. So m of p of x is you substitute square root of x minus 2 for x. Okay, and so what is the domain? Well, x can't be less than 2. We know that. But also, you can't include a value of x that makes p of x equal to 5, because then you'll divide by 0. That's the only domain restriction of m of x, is x is equal to 5. So x can't be less than 2, because this will be a square root of a negative number. But also, x can't equal what? 27, because 27 minus 2 is 25. So the domain is x is greater than or equal to 2, and then but x can't be 27. That's a better example. Okay, here's a word problem. We're going to do some word problem examples in the next video. Yeah, so here is the idea of decomposing functions. And it's just more of you can, the idea here is you can look at a function and get a sense of, like, you know, we a couple of sections ago, we talked about transformations of graphs, and you're looking for that basic function that's underlying the expression. Well, that's in a sense what you're doing. You're seeing, if you have a basic expression and it's been transformed, then there's function decomposition there, right? Because if you have the basic function x squared, so if you have x minus 3 squared, well, that's x minus 3 contained within the basic function x squared, right? So if f of x is equal to x squared, g of x is equal to x minus 3, you can look at x minus 3 squared as f of g of x, right? So all of those transformed basic expressions that we talked about in a couple of sections ago, you can look at it that way. There's function composition that with the outer function is going to be the basic function, like x squared or absolute value of x or x cubed. The inner function is going to be whatever's the transformed part, like x minus 3 or minus x, right? If you had f of x is equal to the absolute value of x, g of x is equal to minus x, then f of g of x is equal to what? See? Or like you could extend this, but you could say, so if you had absolute value of x minus 3 cubed, so g of x is equal to x minus 3, h of x is equal to x cubed, m of x is equal to the absolute value of x, then you would have m of h of g of x. That's equal to f of x. You see, g of x is x minus 3. H of g of x is x minus 3 cubed. M of h of g of x is x minus 3 cubed, or the absolute value of x minus 3 cubed, right? Now, how would you write this in with the composition notation? I guess you would say, so this is h of g of x. So you would do m of h of g of x. You see, this is f of x. Okay, estimating function values from a graph. We'll work some examples like this as well. Let's just give you more intuition of the ideas we're talking about here. Okay, let's work some example problems now.